All right, let's just jump right in. I want you to picture the vast, deep blackness between galaxies. I mean, it seems like the very definition of nothing, doesn't it? Just an absolute, silent void. And for centuries, that's exactly what we all thought it was. But, and this is a big but, it turns out that the most empty space in the universe is actually one of the busiest, most chaotic places you could possibly imagine.
Yeah, so the old school view, classical physics, saw a vacuum as super simple. It's just total emptiness. You suck all the particles out of a box, and hey presto, you're left with nothing. But quantum mechanics, it just blows that whole idea completely out of the water. It tells us that what we call empty space is actually the seething, roiling sea of energy and pure potential.
So, what's really going on in there? I mean, if it's not empty, then what on earth fills it? That is the huge question we are going to unpack in this explainer. And you're going to want to stick around for this because the answer suggests that the very fabric of our reality is woven from, well, from nothing. To even begin to get this, we've got to enter what you could call the quantum underworld. And no, this isn't just a place. It's a whole new set of rules for the game, governed by something called quantum field theory. This is basically the bedrock of modern physics, and it describes a universe that's not built on solid little things, but on these shimmering, invisible fields of pure potential. And this slide right here, this gets to the absolute heart of it. Forget picturing particles as tiny little billiard balls. Quantum field theory says nope. Think of them as ripples, or, to use the official term, excitations in a vast invisible ocean. Every single particle, an electron, a photon, you name it, is just a wave in its own special field that fills every inch of space. So what happens when there are no real particles around? When a field is just sitting there in its lowest possible energy state, what we actually call the vacuum, it's not perfectly still. It's constantly jittering, constantly fluctuating. And out of these tiny fluctuations, something totally incredible happens. Pairs of so-called virtual particles and their antimatter twins spontaneously pop into existence. How in the world is that even possible? Well, it all comes down to a fundamental rule of the quantum world, Heisenberg's uncertainty principle. In a nutshell, it says you can't know both the energy of a system and the time you're measuring it with perfect pinpoint precision. This little bit of wiggle room, this uncertainty, lets the vacuum briefly borrow a tiny amount of energy out of thin air, as long as it pays it back almost instantly. This is that energy loan you see here, and it's just enough to create a particle-antiparticle pair for a fraction of a second before they smash into each other, annihilate, and repay the debt. And look, this isn't just some weird theoretical quirk. These virtual particles are absolutely crucial. They are the invisible messengers carrying the fundamental forces of nature. You know when two electrons repel each other? That's because they're literally playing catch by tossing virtual photons back and forth. Without this constant fizz of activity in the vacuum, our universe just couldn't exist as we know it. Okay, I know. This all sounds like something straight out of science fiction. Particles popping in and out of existence, invisible messengers. So how on earth do we actually know any of this is real? How can we possibly measure the effects of, well, of nothing? The answer is found in one of the most elegant and, frankly, mind-bending experiments in all of physics. It's a method for measuring a real, tangible force that is generated by nothing more than the empty vacuum itself. It's called the Casimir Effect. Now, the setup itself is deceptively simple. You take two perfectly smooth, uncharged metal plates. You put them incredibly close together. We're talking just a few nanometers apart. And you stick the whole thing in a perfect vacuum. Now, according to classical physics, absolutely nothing should happen. They're just sitting there. But remember those virtual particles? They behave like waves. As you can see in this chart, outside the plates, the vacuum is churning out virtual particles of all possible wavelengths, creating this kind of pressure. But now look at that tiny little gap between the plates. That narrow space physically restricts which wavelengths can exist. Only the waves that fit perfectly inside are allowed. This means there's less activity, creating a lower pressure on the inside. And the result? You get a net pressure from the outside pushing the plates together. It's a tiny, tiny force, but it's measurable. And this is the genius of it. It's a force generated purely by the vacuum itself, a force from nothing. It's one of the most direct, undeniable proofs we have that the quantum vacuum is a very real thing. And the Casimir effect isn't some lonely outlier.
There's also the Lamb shift, where these same vacuum fluctuations ever so slightly nudge the energy levels of electrons inside atoms. And then there's spontaneous emission. The reason an excited atom spits out a photon of light? It's actually the noise from the vacuum that prods it into doing so. The evidence is literally all around us, at the smallest scales.
So we've just seen how the vacuum can push things around on the tiniest nanoscale level. But what happens if we zoom all the way out? I mean, all the way out, to the scale of the entire cosmos. Well, if all of space is filled with these non-stop energy fluctuations, that means the vacuum itself must have a colossal amount of built-in energy, even when it's as cold and empty as it can possibly be. We call this zero-point energy. It's the baseline energy of empty space. Okay, but here's where we slam into one of the biggest mysteries in all of physics. When our theorists use quantum field theory to calculate how much energy the vacuum should have, they get a number that is just astronomically huge. But when our astronomers actually measure the energy that's driving the expansion of the universe, they get a number that is 120 orders of magnitude smaller. To put that in perspective, that's a 1 followed by 120 zeros. It's been called the single worst theoretical prediction in the history of physics. This crazy mismatch is known as the cosmological constant problem. Now, even with that insane discrepancy in the numbers, many physicists still think that this vacuum energy is the best candidate we have for the mysterious dark energy. That's the force that isn't just pushing the universe apart, but is actually making that expansion speed up over time. So the energy of nothing could be the very thing shaping the ultimate fate of our entire cosmos. So, we've gone from the unbelievably small to the cosmically huge. But what does any of this mean for us, right here, right now? Can we actually do anything with this knowledge? Is it useful? Oh, absolutely. On the cutting edge of technology, understanding the vacuum is non-negotiable. In nanotechnology, that Casimir force we talked about becomes a real physical thing you have to design your microscopic machines around. If you're building ultra-precise sensors, you have to filter out the background noise created by these vacuum fluctuations. And in the massive global race to build quantum computers, managing these tiny jitters of reality is one of the single biggest challenges we have to overcome. So here's the bottom line, the big takeaway. The vacuum isn't some passive, empty stage where things happen. It is an active, dynamic, and incredibly powerful engine. It's mediating forces, it's pushing objects around, and it might just be driving the expansion of our entire universe. Nothing, as it turns out, is pretty much everything. Which kind of leaves us with one final mind-bending thought. We took a look at what we thought was the most boring, empty thing imaginable, and we found a whole universe of activity. It just makes you wonder, if empty space is this powerful, what other profound, reality-shattering secrets is the universe hiding right there in plain sight, just waiting for us to notice?